Dear students, in this presentation, we will discuss another data structure, that is stack. Here in this presentation, we will discuss the definition, how that stack can be represented theoretically, what is a stack top, what different major operations that we can perform, how to represent stack in memory, like static representation and dynamic representation using arrays concept. There is a difference between array data structure and stack data structure. As we have seen earlier in case of array, where we are able to insert or delete any item in the array. It is not necessary to delete or insert only in one certain end, like the top or the beginning. So we can insert element in any position of the array provided space must be there. Or we can also delete any element provided stack is not empty. So those are we have seen in the last module. Other operations that we have seen under array are traversing, creation of array, like that. Today, in this presentation, we will be diverting our topic of discussion to stack only, stack data structure. The stack is very much important to to store your data or information in the proper order. It is an ordered list. As you know, like in array, each element is also indexed. Okay, that index cannot be a negative number. A major thing that you should note here is that only from one end, you can perform the operation. The operation can be insertion. We call here that with a technical name called push, or we can remove one element from the stack. Technically, that operation is called pop operation. So, stack is an ordered list in which insertion and deletions are made at one end. That end is called top of the stack. These elements are represented with the index value A0, A1, like that, AN minus 1, where n minus 1 is the top element. Number of element in the stack, it is n. For example, if I represent that stack in horizontal way, okay, these are the elements that are already there in the stack. Right now, four elements, we'll assume four elements in the array. Elements are 4, 5, 6, 7. As you can see, there are four elements in the stack. So this is n. Size of the stack is 4. This is also called size, stack size. That is not the maximum size, the current size of the stack. There are four elements, so n is 4. Usually we start index from 0. This is 0th element, this is first element, this is second element, and this is third element. Okay, so this is called top of the stack. The top is size minus 1, size is 4, so top is 3. Okay, this element can only be deleted. You cannot delete 4, 5, 6. So 7, after deleting 7, then we can delete 6. After deleting 6, then we can delete 5, like that. So only one end is open. That is called top end. And the new element can be placed after top. The top current value is 3 at fourth place. Here that new element can be inserted. So the push operation takes in the last end, top end. So that operation adding one element to the stack is called push. Removing an element from the stack is called pop. These are the two major operations that we can perform. Push is the term used to insert an element into the stack. Pop is the term to indicate the deletion operation. The stack is a list of elements in which element may be inserted or deleted only at one end. That is important. Like in array, we can perform operation at any position, but here in that last position, the top only, you can perform push operation or pop operation. This is very much important. Top of the stack is very much important. Okay. The last element that is entered into the stack is going first, is deleted first. That is why the stack is also called last in first out list. It is a list, last element that is entered. For example, if I push 8 to the stack, only this 8 can be removed. The last element entered into the stack is 8. The first element that will go out of the stack is also 8. That is why it is called last in first out. Last in first out list. So this is another way to indicate stack is last in first out. Okay. How theoretically the stack can be represented? Suppose my stack size is 5. Elements are 10, 20, 30, 40, 50. I can represent horizontally where index is in increasing order. Index 0 or the address is in increasing order. 0, 1, 2, 3 and 4. The stack top is 4, stack size is 5. Only this element can be removed or to this position item can be added. Top of the stack is 4. This is one way of representing the stack. Sometimes we start with the lower address. For example, if I take address as 1000, we call this as the base address of the stack 1000. Index says you know that it is 0, 1, 2, 3 and 4. These are the index. The address, if it is integer, each takes 4 bytes. 1000, 1004, 1008, 1012 and 1016. As you know, as you can see, the address is in increasing order. Usually we start with the lower address. Stack grows from lower address to the higher address. That is one way of, another way of representing. Sometimes we also initialize stack with the higher address. Highest address is used to initialize the stack base of the stack. But when you perform insertion operation, each time address is decremented. Highest address is used. For example, if I take 998 or 1000, I can say 1000. If 1000 is given for the base of the stack, then for the next element it is 996. 996. Why 996? Because as taken stack is in decreasing order. It grows in the decreasing order from higher address to the lower address. Highest address to the lower address. 1000, 996, 992, like that it goes. Starting from higher address to the lower address. This is one another type of representation. Any type you can use. It all depends on the purpose or the application. Usually for system program, no, stack is used with the highest address. It grows in the decreasing order of address. These are the three different representation of the stack. Okay, this is theoretical representation. Sometimes we use the lower address, sometimes we use higher address for stack base. Why the stack is called last in first out? Stack, as you know, it is a finite set of elements. In many cases, that size is also infinite. But for our explanation purpose, we'll take stack is of fixed size. Stack capacity of fixed size. Say 5 elements. Okay, we'll take stack size of 5. Hardly, at the most 5 element can be stored. Right now, in the first case number 1, where we don't find any element, in that case now, top is not there, top is set to -1. That -1 value for the top indicates that stack is empty. Stack is empty. Empty condition of the stack is indicated with the -1. That you have to remember. Then I'm going to insert the first element. We call here technically push operation. I'm going to push A to the stack. Where that can be placed? At the top. Top value is -1. We can't have -1 as the index value. That's why increase that index -1 plus 1, that is 0. To top place, top value is 0. Earlier it was -1. -1 plus 1 is 0. To that place, new element is inserted. So top is now here. So what you have to do for insertion, increase that top value. If you started the top with the -1, always increase the value of top or update the top value, then insert it. If you start with 0, insert the element, then update the top value. Anyway, it is all depends on the implementation. Okay, in this case, I have taken -1 value, that initial value as -1. So I have to update the value of top, then I have to perform push operation. Otherwise, it's also possible. The second element that I'm going to push into the stack is B. The top value, current value is 1. Okay, current value was 0. Now increase it first. Update the value of top. Top becomes 1. To that position, insert the value. Push the value. Top value is 1 now. Now we'll see how to push another element. See. So each time when you are pushing, you have to see that whether it is crossing that limit or not. Whether we reached the full, the last top index of the stack or not. Whether stack is full or not. We cannot accommodate another element if stack is full. That condition you have to check. So now we'll see that condition. The maximum capacity of the stack is 5. Right now there are two elements in the stack. Can I push one more element? Two elements are there in the stack. The maximum capacity is 5. Still 3 more elements I can accommodate. That means insertion is possible, push is possible. What was the top value? Top value was 1. Increase it first to 2. To that place, new element is pushed. That new element is C. Okay. Now stack capacity, maximum capacity is 5. Stack size is 3. We'll see one more push operation. The new element to be inserted is D. Can I perform push operation? We'll see. There are 3 elements. Maximum capacity is 5. I can accommodate 2 more elements. Yes, I can push D into the stack. What was the top value? Top value was to increase it first, update it first by adding 1, 3. To that place, that new element is inserted, D. We'll see the last one more push operation. The element to be pushed is E. Now, the capacity at this part at this time is 4. Maximum capacity is 5. Right now it is 4. The maximum capacity of the stack is 5. Right now there are 4 elements. Can I push one more element? Yes. There is one more free place. In that place, I can perform push operation. Now, what is the element to be pushed? E. So here what is required? The current top value and the maximum capacity. So you subtract that. Otherwise, you just check that top is 1 less than the max value. We'll see that in the next case. So here I can perform push operation. Now the capacity of the stack is now was 5 and the number of element in the stack is 5. The maximum capacity is 5. Current elements, number of elements in the stack is also 5. Now we'll see whether I can push one more element, say F. Okay. Now, what is the capacity of the stack? 5. What is the top value? 0, 1, 2, 3, 4. Top value is 4. Is it 1 less than the capacity? 1 less than the capacity. Top value, is it minus the max minus 1? Max value is 5. 5 minus 1 is 4. Top value is also 4. Max minus 1 is also 4. That means there is no space in the stack. Stack is observed full. It is full. I cannot perform push operation. F cannot be pushed. So the system should give stack is full. Insertion is failed. Okay, now we'll go for deletion. Should I tell what element to be deleted? No need. Whatever the element is there at the top, that I can remove. I need not mention even the index also. Like in case of array, we need to we need to supply which element that you're going to remove. Index is important, but here the index is not required. Whatever the element is there at the top, that is removed, that is popped out of the stack. What was the element at the top? E. That is going to remove. So it is a delete operation. After delete operation, the top has to be updated. Earlier it was 4. After the delete operation, top is now decremented by 1. 4 minus 1, that is 3. So theoretically, in this way, the stack must be implemented. Okay. Now, I will take this condition to remove an element. What is the maximum capacity of the stack? 5. Let it be. What is the top value? Minus 1. I want to remove an element. Can I remove? Element is not there. Can I remove the element? So the system should say that deletion failed. I cannot perform deletion operation. So what is the condition to be checked? Is top value is minus 1? If so, is top value is minus 1? If so, deletion cannot be performed. So in short, I can tell like this: when push should fail, when push cannot be performed, if push cannot be performed, if top is equal to max minus 1, if top value is 1 less than the max value, then that observes full status in the stack. Push cannot be performed. Otherwise, push is okay. In the same way, pop cannot be performed if pop should fail if top equal to minus 1. Top equal to minus 1 indicates stack is empty. How can you delete the element if stack is empty? That is a condition. Otherwise, that indicates that there is some element there, more than one element in the stack, or more than at least one element in the stack, we can delete it. This is how the stack works. Now, before implementing stack, we'll see the importance of stack, how a special type of stack is maintained, how that is used. You know that if main can call a function or a function can call another function. So when you are executing, when the function executes return statement, the control has to be transferred back to the calling part, the caller. If main is calling, suppose main is calling a function f, operating system invokes this function main calls f. So there will be a return statement. If no, there will be a default return statement is added, and that time the control has to transfer to main program. That means the return address is very much important. Return address is the address that is after the call statement in the calling part. Okay, so that is like this. There is a main program. Okay, this is the starting point of the main. I will take address 1 2 3 just for reference only. At this place, function f is called, function name is f. Okay, here program is ended. Function when it is called, so that function body goes like this. Function, the last statement is return address. When return is executed, the statement following the function, that means this has to be executed. This is called return address. This address that is after the function call. Function name is f. F is called, control transfer to function. There will be a return statement. The control comes back to this statement. This one. This is called return address. Remember that. Return address. Caller, calling. Who is calling? Main is calling. What is invoked? Function is invoked. So now some information has to be maintained in the stack. Okay. So that stack is not created by the user. That stack is called system stack. That stack is called system stack. Okay. So that another name is also used, that is activation record. Activation record or stack frame is created when our function is invoked. So when function main is invoking function f, at that time stack frame has to be called. Where is the place of that one? So system will keep aside a part of memory for this purpose. That memory is called stack memory or stack frame, stack, system stack. It is not at all used by the user program. It is used for this purpose. Stack frame will be placed on top of system stack. So a stack is reserved in the memory. Memory has memory the user memory is divided into so many parts. One such area is called system stack. This area is reserved. The top part is reserved for stack frame. Okay, that means highest address is reserved for that purpose. The system, the stack frame pointer points to the stack frame of the invoking function. Okay, whenever a frame is created, a pointer is used a pointer is used. We'll see that in the next slide. A pointer is used that points to stack frame of the invoking function. Suppose main is the operating system calls main program, a stack frame is created. That information is added here. The local variables of the function, then parameters, all those informations are put here. When main calls another function f, a frame is created. This is the stack frame for, or this is the activation record for the function. So that there will be a pointer here. The last part is that pointer, that is stack frame pointer, that points to invoking function. For this invoking function is main. There will be a pointer here. The last part is pointer, that is there in the next slide. The return address which contains the statement to be executed after the main function. When it terminates, when f terminates, what to be executed? The statement after that calling part in the main, in the calling part, no, that is going to execute. If a function is invoked, its local variables are added into this stack frame. So when the function is over, when function terminates, this will be freed. That frame will be freed. Okay, so retaining only this part. When the main function is also over, this is also freed. We'll see that here. Now assume that main operating system calls main. At that time, one stack frame is added. All the variables of main, the parameter that is passed to the main are added. Now what happens? So this is a minimum requirement. Just for simplicity, I took only these information. Still many informations are there. At this stage, it is not necessary to know all the things. Okay. Now, this is the thing when main is called by operating system. Invoking function is operating system. System stack is used. This is before calling A1. Operating system calling operating system function calls main. At that time, this is the situation. This is the function pointer for main. So this has got the return address. When function is over, when main is over, it has to go to somewhere else. That is the statement to be executed. That is the address. That is called return address. So main has to return. It has to transfer its control to that part. That is the return address. Okay. Now what happens when function is the main is calling a1? This is the thing. This is the thing. So main function is calling a1. Here we don't have any parameter. Here we don't have any local variable, but stack frame has to be created. Activation record has to be created. What all things are there in that record? One is frame pointer, which is pointing to the return address. See, when function is over, when A1 gets terminated, the control has to go back to main program. So that return address, when A1 get terminated, it has to transfer the control back to the calling part, that is to main. That is why it is given frame pointer. It has to go to the main. All extra things are given, right? Like local variable, parameters are all given in this part. Again, one more example there in the next slide. We'll see how that happens. Now, operating system invokes function, the C application. Activation record is created in the system stack. This is done by at the time when main is called, main function is called, this program is called in the next stage. So these are some statement. A is called. When A terminates, this has to be executed. This is called return address 1. Okay. When A terminates, the control has to come back to this place. When B terminates, control has to come back to this place. When C terminates, it has to come back to this place. This is return address. This is also return address. Now we'll see what happens when A is called by main. Before going to A, before going to call A, activation record of the main is created. So this is done at the time when main is invoked by the operating system. When A function, the function A is called by main, activation record of A is created like this. This is the situation, this is the status of the system frame, system stack frame when main calls function A. Okay, the same way it goes. A is now here. The control enters to function A. There are so many statements, local variables, parameters, so many statements. Now, what happens when A is going to invoke B? Another stack frame is created. Another stack frame is created. There it puts information about B here. Okay. When B invokes C, when B here it is invoking C, another record is created like this. Another record is created. This is for C. This is for B. This is for A. This is for main. Okay. Another activation record is created. There it puts local variable, some other information, parameters, all those necessary informations are put here. Okay, now what happens when C terminates? The last statement will be usually return statement where control is returned to the calling part. That time now this will be removed. The whole thing will be removed. Okay, now in the system stack we find only three information: activation record of B, activation record of A, and main. When C terminates, it comes back to B, the top of B. Okay, now assume that B is also getting terminated. This will be removed from the system track. That means control comes to this part. Control comes to this part, not this one, this part. The statement after this calling part. When that is also executed, this is removed. Then that means control is transferred to the main here, here. Okay, return address. When main function is also over, this part is also removed. This part is also removed. This is how the activation record or system stack works. Okay. So this activation record is another name used for the system stack frame. It is a data structure that composes calling stack, call stack. It is generally composed of local to the calling and the return address. Return address. These two informations are put. Activation record format is static because size is growing. Record is static, but we don't know how much to allocate. That is known only when it enters to the function. An instance is created. An instance is created. This is all happening at the time of execution. It is created dynamically. During execution, this activation record is created. During the execution only, it is getting created. So it is dynamic. Now we'll see another example. Operating system calls main. Main is invoked by the operating system. Now what happens? Activation record is created. As you can see, there is a local variable p. Local variable p is declared here. P is put here. This is the activation record for main. Okay. Now main is calling the function 1. It is sending a parameter p. The local variables are t and s, argument is r. Now what happens at this stage? Activation record is created. Okay, activation record is created. A dynamic link is added, that is a link to the previous record. Dynamic link, that is a link, it is a pointer to the previous record. This is the last one is the pointer to the last record. Okay, these are the things. Another record is created. What are all things? Return to the main. So when the function is executed, it has to go back to the function. So return address is required. Then a pointer to the previous record. Then what is the parameter sent? Parameter name is R. Parameter. Okay. Then what are the different local variables used? T and S are the local variables used. So these are the different informations that are maintained in the activation record. Return address, a pointer, the parameter, and local variables. We'll see. One more. Function 1 calls function 2, where it is sending parameter t. The local variable t is sent as a parameter to the function 2. Another record is created. Another record is created. So another activation record is created. So here when the function 2 getting terminated, it has to go back to this part, that is the return address. Return to function 1. Dynamic link to the previous one. Dynamic link to the previous record. Here this one. Okay, then what is that parameter sent while calling? T is the parameter that is sent at the time while calling. But in the function definition, x is a parameter. Y is the local variable. Y is the local variable. So this activation record has got 4 information: return address, dynamic link, parameter list, any parameter, any number of parameter, local variable, local parameter, dynamic link, return address. Okay, then we'll see when function 3 is called. Function 2 now invokes function 3. Function 3 is invoked by function 2. Another activation record is created here. Again, same for information. Return to function, then the link, parameter. Okay, so like this, one more is created here. Here, one more record is created. Return address, dynamic link, the parameter, that is q, only this much, because there is no local variable. This is the last activation record created at point 3. Okay, point 0 and OS calls main. Point 1 when main calls function 1. Point 2 when function 1 is calling function 2. Point 3 when function 2 is invoked. Function 3 is invoked by function 2. Okay. Then we'll see what are the different ADTs required, abstract data types required. Okay. For all the stack, each item that is of type element, each item of type element, here you have to define the maximum capacity of the stack, which is a positive number. 10, stack size is 10. It cannot be a negative number. Okay. So there is an ADT which creates the stack. You know how to create the stack. In C programming, array concept can be used. Dynamic memory allocation, that concept can be used. Purpose is to create the array, to keep some set of memory location to put elements of the stack. That is stack creation. So when you create an array, when you create a stack with that size, that means all elements are initialized. No elements are there in the stack, but memory is reserved. How much is reserved? This much space to accommodate these many elements at the max. Suppose the maximum capacity is 10 and each data is of type integer. 4 bytes in C, 40 bytes are reserved. 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 The maximum capacity is 10, but no element in the stack. The capacity of the stack is 10. Each element takes 4. Total of 40 bytes are reserved. So that returns a stack. Stack creates with this size. Okay. Second, we should know when it is not possible to perform push operation. When stack is full, we cannot perform pull operation. We have to test that condition. We have to test that condition. That condition is tested using an ADT called is full. So that returns true or false. Now in this case, is stack is full. Right now just created, brand new stack is created. No elements are there in the stack. I can perform 10 push operation. So in this case, stack is not full. So it should return false. Suppose that the stack is having some 10 elements. 10 elements. That means stack capacity is also 10. The number of elements in the stack is 10, which is equal to the maximum size. Number of elements in the stack is 10. If that is also equal to max size, in such case, true should be written. That indicates that stack is full. Okay. Next ADT is to test whether stack is empty or not. Suppose this is my stack, the maximum capacity is 10. Can I perform pop operation? As we don't have any element in the stack, the pop operation should not be performed. So how it is possible to know whether it is empty or not? In this case, some function, say empty is empty function, should return true because no element is there in the stack. Number of element in the stack is 0. Number of element in the stack is 0. Okay, so stack number of element in the stack is 0. In such case, that indicates that stack is empty. Return true. Suppose one element is added. Is stack is empty? Maximum element in the stack is 10. Right now only one element in the stack. Can I perform pop operation? Why not? You can perform. This element can be removed. So when your testing is empty, when you're testing at the stage when your testing is empty, it is returning false. That indicates that stack is not empty. It is having at least one element. Okay. Then two different operations we can perform at stack top. One such is adding element. When we can add the element, if stack is not full, if is full is false, is full is false, that means that stack is not full. We can perform push operation. Assume that stack capacity is 5. We'll see now. Is stack is full, the maximum capacity is 5. Number of element in the stack 1, 2, 3, 4, 5. No element in the stack. Is it same? 0 and 5 are they same? No. So there is no question of that stack is not full. There is no question of displaying this part. That means we can perform insertion operation. Assume that new element to be inserted is 10. That 10 comes to this place. After the insertion operation, stack top has to be increased. Okay, stack top has to be increased, has to be updated. Now I'm going to perform deletion operation, pop operation. Just check whether stack is full or stack is empty or not. Is empty is called. Is empty will check and compare the number of elements with max with 0. The number of element in the stack is 1. It is not 0. That means false is returned. So the stack is not empty. Stack is not empty. Sorry, stack is not empty. That means this element can be removed. If stack is not empty, that indicates that at least one element in the stack, the top element can be removed. After the operation, again you have to update the stack top value. After the insertion, stack should be increased. After the deletion, stack top should be decreased, decremented by 1. Decremented by 1. We'll see how that is actually done in C. We'll create a stack which can hold up to 100 elements. The create function. Okay, the create function will use stack to hold a structure. Okay, for the simplicity, we'll take a structure of one member. Any member we can add it. Will have only one element that is of type integer. We can store student information like roll number, USN, name, age, date of birth, dash 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 dash. All those information can be stored. Here, just for the simplicity, I took only the roll number, that is integer type field. Okay, as it is a stack, number of elements are more. So this is of type element. This is of type element. So for that I need to create array. I need to create array of these elements up to 100. Stack of 100. That means 100 at the most 100 elements I can store. Not more than that. So this is the maximum capacity of the stack. Okay, and I'm assuming top value -1. That indicates that stack is empty. Top equal to -1. Now, one more function, that is empty function. If top value is less than 0, as I told, top value is -1, that indicates that stack is empty, returns true. If top value is less than 0 or top value is -1, return true. In the same way, another ADT that is full should return true. These are all not exact C program. Return true. When to return? If top value is 1 less than the max size. 1 less than the max size. If stack capacity is 3 and 3 elements are there, number of elements, stack top is set 2. When items are filled, the top value is 2. Is it 1 less than that max value? Yes, return true. The next is adding the element. Okay, what to add? To this stack, at this place, the new element has to be added. So we need stack. This is the current status of the stack, having say 2 elements. This is the first element, this is the second element. The new element to be added is 14. Say the top value. What is the top value? Current top value is 1. Current top value is 1. Now you have to test whether stack is full or not. Assume that the maximum capacity here it is 5. We'll assume that stack capacity is 5. Stack top value is 1. 5 minus 1 is 4. Is it 4? No. That means stack is not full. So what you have to do? Increase the value of top. Top value was 1. Now change it to 2. Top is increased by 1. Top plus plus. Top value was 1. Now top value is 2. In that place, new element you have to copy. That new element is a 14. The 14 will come here. The top value is updated. Top value is 2, that is updated. What you passed? 1. What is the recent value of top? It is 2. Now, we'll go for the deletion operation. From where you have to delete? From this array you have to delete. we should know the top value. We can return the element. This is not necessary to pass. This is not necessary to pass. So you have to return that item that is written. Okay, we'll see now. A stack capacity of 5. Now, no element is there in the stack. The capacity of this, the current number of element is 0. Is stack is empty? Yes, stack is empty. So you can't perform pop operation. Other case will take. My elements in the stack are 10, 20, and 30. I will go for deletion operation. Top value is 2. Okay. Is top value is -1. That's what. Is empty is testing the top value with, is it less than 0 or not. It is not less than 0. It is not -1. That means it is not empty. So what to do? Pick up this element 30. Item value is 30. Then top you have to decrease it. 2 minus 1, that is 1. Return the element 30 you are going to return. So now this is removed. This is the updated status of the stack having two elements 10 and 20. Okay. Now we'll see how to implement the stack using array concept in C. A structure is defined, type depth, struct element with only one field just for the simplicity. The max value say 100. Stack is created. Each element of type element structure. We have initialized top equal to -1. We can perform push operation. We can perform pop operation. For push operation, element to be pushed is passed. In case of pop operation, that is returning the element that is removed from the stack top. The function is easy. In case of push, you are going to pass an item. Check the value of top. Is it max -1? If so, it is full. Otherwise, increase the top value. Copy that element. Okay. Now we'll take that example. There is a stack. The maximum capacity is 5. Okay. Assume that there are two elements in the stack. Maximum capacity is 5. The top value is now 1. After, before to this push operation, the new element to be inserted or pushed is 6. Check it. Top value is 1. Is it greater than max -1? Max is 5. 5 minus 1 is 4. Is it 4? No. Stack is not full. Increase the value of top. Plus plus top. Top becomes 2. In that place, item to be inserted. That is 6. Insert it. In that place, insert that element. Okay. Top is updated. Item is inserted. A prompt saying that the top element that is inserted. Stack of top. That is 6 you're going to see. Then we'll see now how pop works. I'm going to remove the top element from the stack. Now I have to check whether top is -1 or not to see whether stack is empty or not. Stack top is 2. Is it -1? No. That indicates that stack is not empty. Stack is having some elements. Okay. Return stack top. So top has to be decreased. Later after returning, no, top has to be changed, has to update. 2 becomes 1. What is the element that is removed? 6. 6 is popped out. Top value now updated to 1. Okay. After the deletion operation, the stack is having only 2 elements. This is the stack. Okay. Top value is 1. Capacity is 3. This is after push pop operation. So to test that now, this can be used. We'll see how that works. Demonstrate that. Item 2. I'm going to pop. Right now, stack is created having say 5 elements. 1, 2, 3, 4 and 5. I'm performing now pop operation. Can I perform pop operation? This is the status of the stack. Can I perform pop operation? No, because top value was -1. We observed stack empty. I can't perform stack pop operation on stack. So you'll get stack empty. Okay. Then I'm going to insert one. I'm going to push one into stack. Item one is going to push. Item one dot key is equal to one that you set it. Pass that item one to push function. Push function takes element as input, item as input. Now top value -1. Is it max -1? Max value say 5. 5 minus 1 is 4. Is it full? No, stack is not full. So top is incremented plus plus top, that is top is 0. In this position, this element is inserted, that is 1. Okay, so successfully we inserted 1. In the same way, go for the second element. Element is 2. Just check whether stack is full or not. Top value is 0. Is it max -1? Max value is 5. 5 minus 1 is 4. 0 is not equal to 4. That means this element can be inserted in the last place too. Okay. The next element is also same. Like that, you can try few more attempts like push operation, pop, pop like that. Okay. Add few more lines and test this program. So the problem with the static is that we have to reserve the memory location, even if you use or don't use. That is immaterial. When we don't use the stack and heavy the large capacity stack is maintained or initialized, no size getting wasted. Now we have to find out some other method so that size can be saved, memory can be saved. So here we go for dynamic memory allocation. Memory is allocated as and when you want. Initially you create a smaller size stack, say of 2 elements. When we observe stack full, for further push operation, don't ignore that push operation, but expand the stack size. You make it double, then go for push operation. Anyway, initially, I'm going to reserve a small capacity stack, say 2 elements. Assume that after 2 push operation, the elements are 2 and 3. Now, I want to push another element into stack 4. This data is very much important for me. I have to store that in the stack. I cannot reject this data. But there is no space. What to do? For that, we use now dynamic concept. What is the current capacity? The capacity is 2. You make it double. 2. Okay. Re-alloc. This can be done with the malloc or Sierra function. Re-alloc. Double the capacity. Now capacity is changed to 4. 2 more elements can be taken. So my next element to be pushed is 4. So when we observe stack full now, increase the capacity of the stack. So you are utilizing the memory. You are not simply wasting the memory. If required, expand it. Okay, I'm going to perform another push operation. Yes, I can. No problem here because we already made array capacity of 4. Now I have to perform push operation to push 10. If that is the previous case, no, this 10 will be rejected. You are unable to perform push operation. As it is a dynamic concept, we expand this array by doubling the capacity. Current capacity is 4. Double it. Becomes now 8. 4 more locations are there. This 10 can be saved. This 10 can be pushed. This is how dynamic memory concept, dynamic array works. This is very much important for the exam point of view as well as implementation point of view. My array is of type element, which is a structure having only one member. Okay, I'm going to create a pointer for that, stack pointer, initially null. Initial capacity is 1. When one element is added, make it 2. When two elements are added, make it 4. When four elements are added to the stack, make it 8, like that. Each time capacity is doubled. Top value is -1 initially. So two important functions that you are going to implement are push and pop. Push little bit different. If we observe the stack full, that is capacity -1, realloc the stack name is stack. How much to allocate? Make it double earlier capacity into 2, capacity into 2. That may be number of for each element, size of element. If each element take 4 bytes, 4 into 2 into old capacity. Old capacity was 1, 1 into 2, that means capacity is doubled. 2 into 4, 8. That size is now doubled. So update the value of capacity. Capacity earlier it was 1, after this doubling, make it double. Capacity into 2. In future, the capacity 2 is taken. When two element is also added, when we have got two elements, make it double. Should be a 4, like that. Then rest of the things are same. Increase the top value. In that place, insert that element. As it is a pointer, use arrow operator. Arrow operator. If it is not a pointer, then dot is okay, like previous case. Increase the top value. See, in the previous case also same thing. Top is incremented, then it is inserted. First increment, auto increment is done, then assignment happens. Here also same thing. First incremented, then to that place inserted, item is copied. Remember to use arrow operator because it is a pointer. Okay, next pop is same, no difference in the top value. Print that value, change the top value. If top is -1, that means we observe emptiness in the stack, no element in the stack. Okay, how to call that? First you have to allocate memory location. As I told, initially capacity is 1, 1 into size of that element. If each element take 4 bytes, 4 bytes are reserved. This is the initial capacity of the stack, 4 bytes. Perform pop operation. Is it possible to perform pop operation? Top value is -1. If it is -1, stack is empty. Yes, stack is empty. You can't perform pop operation. The message that you will get is stack is empty. Go for 1. Inserting 1. Can I insert? Top value is -1. Is it equal to capacity -1? Capacity is 1. 1 minus 1 is 0. Top value is greater than that? No. Stack is having enough space to put new element. New element is 1. 1 is put here. Top is now 1. Top value was -1, now it is 1. Sorry, now it is 0. Now it is 0. Top value was -1, now it is 0. We'll go for pushing 2. Can I push the element? See, top value, is it greater than that? No. That means we have to double it. Earlier capacity was 1, now change it, make it double. 1 into 1 plus 1 is 2. So this is the new size of the array. Because of this realloc function, it doubles the capacity. Capacity was 1, now it is 2. Still there is a space, 2 can be pushed. So when you are trying to push 3, we observe stack is full. But don't reject that one. Reallocate. Realloc happens when you observe stack full. Capacity is now doubled. That new element is added. Even for this also we can accommodate. When you're trying to perform another push operation, actually it is not possible, but it will not be rejected. Instead, capacity is doubled. 1 2 3 4, then elements are added. This is very much important. This part is very much important for the exam point of view as well as implementation. Here easily we are managing. This is the best way to program. Here efficiently managing the memory, there is no wastage of memory. Otherwise, no, we have to reserve the memory location. Suppose In case of static, if you reserve 10 and only 10 elements can be pushed, if the 11th element is very much important, that cannot be taken. It has to be rejected. That is a problem. Case number 2, if we have only one element need to be inserted, then remaining 9 elements, 9 spaces are simply wasted. So there are two drawbacks. If there are too many elements to insert, that will not allow you to insert it. When we don't have sufficient number of elements, too much memory spaces are wasted. But in case of dynamic allocation, you are managing the memory properly. Okay, we'll see the other topics of stack in the next presentation. Thank you.